All right, and now it's time for our guest. Emily Lakdawalla from the Planetary Society is back. Emily,
Hi, good to be here.
it's been a long time since you've joined us here on the Weekly Space Hangout. Go sometime participant, but now got an important project that you want to let us know about.
I do. I wrote a book.
Nice. Awesome.
It's got 400 pages about curiosity and 200 pictures. So there's a lot of stuff in here.
Now, we had known for a while that you had been working on a book about curiosity. You let us know early on as that project came your way and as you were grinding your way through it. But here it is. It's actually in print form. How did it go?
Well, it turns out it's kind of hard to write a book about the most complicated spacecraft ever sent beyond Earth. It's really very complicated. No one person knows everything about it. And so it wound up taking about 3 years longer than I expected it to. And it accidentally turned into two books instead of one. But so the first one's out, though, or at least it should be available in ebook form now from the Springer website. And it's allegedly beginning to get printed and should be available by early May from Amazon and Springer.
So give us the I guess the subtitles. Or give us the title of the book
Yeah.
and then go into the details.
So it is called The Design and Engineering of Curiosity, How the Mars Rover Performs Its Job, which is a very long title. I wanted to call it How Curiosity Works, but that's not how academic publishers work. So they want a nice for search engine optimization. It's a lengthy title for a book that describes basically everything anybody could ever want to know about how this spacecraft operates, or pretty much everything. So it's how the mission came to be in the first place, how the development process happened, and all the pitfalls and all the problems that happened along the way, how launch, cruise, entry, descent, and landing all worked, including very detailed descriptions of all the parts involved. A fairly brief mission summary, and then several chapters devoted to how every part of the rover works, all the engineering parts, the electronics, all the science instruments. And in the back, there's a very big appendix with information about what happened on every sol of the mission up to sol 1800 or so.
I I heard someone say that it was sort of like that you brought more information together in one place than probably anybody who's even worked on the mission knows of, that it is all in this one location.
I would argue that that is true. I basically wrote this book. I wrote the book for the people who like to read my blog. So they're people who like space and are just always seeking more information. They want to have more answers to their questions. But I also wrote this book for the scientists who are working on the mission who don't actually know how the rover works. I wrote it for the engineers who know how their part of the rover works very, very well, but they may not know how some other part of the rover works. And I'll tell you that the people who I was really interested in serving are the hapless first and second year grad students who are starting to work on the mission with some investigator who have no idea what's going on, and this whole thing is so complicated. And so I'm hoping that I will help some of those people along the way to help get them started working on the mission.
I mean, this is the kind of book that if Mark Watney needed to rescue himself and found curiosity, this would be the book he'd pull up to try and figure out how the thing works inside so that he could, get it to communicate with Earth again.
Maybe not quite that much detail, but I do I have to read the blurb that Ashwin Vasavada wrote, and Ashwin is the project scientist on the mission. He writes, if the Curiosity rover had a glove compartment, you'd find this book inside it.
Right. So if you're tinkering on it, you want to know
right.
how the various electronics relays work, then that's the place to go.
That's not in here, but the kind of stuff that is in here is, when did the wheels start having problems? How did they solve that problem? When did the ChemCam focus laser fail, and how did they fix that problem? How did ChemCam work in the first place? What wavelengths of light is everything sensitive to? Why does the rover drive so slow? Why does it take so long to plan? All of these things, all those answers are in here.
I mean, I can just imagine how complicated the research part of this book was. What did you have to do to get some of the answers?
Most of it is actually in the public domain. It's just kind of hard to find it all. But there's, for science, obviously, I'm a scientist, so I have a pretty easy time navigating through the papers describing all of the science instruments and all of that kind of stuff. Engineers, it turns out, don't do so much writing. They typically write things up for like an IEEE conference, the International something engineer something or other. I have no idea what IEEE stands for, but there are conference
Electronic
abstracts.
engineering. Yeah.
Somebody can look it up for
Yeah.
me.
I'm sure someone's going to say it in the chat in a second.
Yeah, but I don't have access to those. And so I started having to email people and kind of through references in one, finding other engineers, getting email addresses, and I at least could get all that information. Those have been vetted by the document review office at JPL, which makes sure that you're not giving any secrets to any other countries who should not have those secrets before they publish this kind of information. And so in order to be able to interview engineers, and I interviewed a lot of engineers for this book, I had to sign a non-disclosure agreement with JPL that said that every chapter of the book would go through document review also, just to make sure that I wasn't going to give any secrets on robots to any rogue nations.
That's a level of scrutiny that I don't think most people would need to receive on writing their book about a robot. But
no, and most of the book didn't actually receive a very deep level of scrutiny, but when it came to the chapters on how the engineering components worked, that one they actually took 6 months to review it. So it's been inspected, detected, selected, and protected.
That's awesome. So there's got to be some great anecdotes that you've got about stuff that maybe you didn't realize how interesting it was until you kind of cracked open the topic.
Yeah, so I think the most amazing piece of information that I discovered along the way is that there was a spare part from the shuttle program that is now crashed on the surface of Mars. So there is a fuel flow regulator from, I think it was Space Shuttle Discovery, that after they retired the shuttles, they were decommissioning them. They were taking out the propulsion parts. They were putting parts of the rocket engines were being reused in the Constellation program and stuff like that. And they had this high volume fuel flow regulator, which happened to meet the specifications of what they needed for the descent stage for the Curiosity mission. And so they pulled it out of mothballs and they refurbished it for Curiosity. It was attached to the rover. They flew it to Mars. It helped lower Curiosity down to the surface, cut all the ropes, then fired the rockets full speed to take the descent stage away from the rover and crashed it on the surface where it actually blew up because there was a lot of fuel left. So there's a piece of the shuttle that was saved and then deliberately blown up on the surface of Mars.
That's great. How are the wheels doing? You brought this up earlier.
Yeah, the wheels are actually doing quite good. So what happened was when they landed on a surface that was the kind of surface they had designed the wheels for, mostly sandy surface with some loose rocks strewn around, and that kind of surface wheels have no problem with. But about 350 sols into the mission, they started putting a lot of miles on the wheels, and they were deliberately driving on the tops of ridges so they could have real long distant views, which is what they need to plan fast driving. And it turns out that the resistant tops of the ridges had very hard rock that was very pointy, wind eroded into ventifacts. And the most important thing was that those pointy rocks were solid parts of rocks. They weren't just loose pieces of rock that could roll around under the wheels. Engineers described them like shark's teeth embedded in concrete. And so when the rover started driving over those, just having a wheel drive over one of these won't cause a problem. The wheels are strong enough not to poke into it. But because of the dynamics of the wheel system, there would be like a wheel on the end of an arm, and it would get pushed onto this, and then it would get shoved in as the other wheels were rolling it forward. And so that is what started damaging the wheels and poking the big puncture holes in them. And so they realized this pretty quickly and realized that the way to deal with it was prevention. And so they had to stop driving on the tops of those ridges. They had to get into safer territory. And it wound up being kind of a cool story, about how the science team used orbital images to map not just for geology, but also looking for wheel shredding rocks. And there's actually now a scientist, a tactical role on the mission called the surface properties scientist, whose job it is to sit at the elbow of one of the engineers and say, that terrain over there is not safe, avoid it, you should drive around over there, and then you can get to, and that terrain is not wheel shredding. And so by doing that, they've actually dramatically reduced the rate of damage on the wheels. And I think there's little doubt that the wheels are going to survive as long as the rover does.
And then future missions will be able to take advantage of this little piece of knowledge for their wayfinding into the future.
Yeah, Mars 2020 has different wheels.
It has those like chainmail looking ones, right?
No, it doesn't. It has, they actually look like a cross between Curiosities and Opportunities. They're a little narrower and they have treads set more closely together.
Right.
And so they'll be stronger and stiffer. That's the other thing, is that the Curiosity's wheels were deliberately made very thin and flexible because it's the landing gear for the rover. And so they were made to deform a lot and then return to their shape. But it turns out that deformability, when you bend a paperclip back and forth and back and forth and back and forth, it finally snaps. It leads to just tears, just rips that are caused by fatigue. And so the new wheels on 2020 will be thicker so that they won't bend back and forth so much, and there will be less fatigue.
Right. All these lessons learned.
Yep.
Arjon's got a great question in the chat, which is, well, his first question is how many different experiments can Curiosity do, but have there been any experiments done that it wasn't originally designed for? And I think that's one of my favorite parts about some of these science missions is when they figure out how to make a spacecraft find something that it wasn't originally intended to do. So how's Curiosity been in that department?
Yeah, there's been a couple of cool ones. One is I think more fun, and that's the ChemCam instrument. So the ChemCam is the laser beam on the rover's head. It fires a laser, it turns a little bit of rock into plasma, and it has a spectrometer that looks at the colors in the plasma to identify the elements that are in it. And because the laser only vaporizes a really tiny point, they attached a camera to it that can take a little context image that shows you the rock area around where they zapped. And there's another interesting piece of trivia. The camera instrument is a flight spare of one of the cameras from the Philae lander on the Rosetta mission. So that's kind of cool. But backing up, so ChemCam has this camera that is mostly used for taking context pictures. But because its focus laser broke, they developed a new way to focus it that actually allowed them for the first time to focus it at very long distances. And so now they use it like a spyglass. They can take incredibly distant images, and they've been studying like this alluvial fan at the distant rim of the crater. Recently, they've been taking a lot of really gorgeous mosaics of the drumlin, or the not drumlins, the yardangs, the wind-eroded hills at the base of Mount Sharp. And so that's a really fun use of the ChemCam instrument. But probably the coolest science that wasn't originally intended comes from the ChemIn, SAM, and APXS instruments all working together to do age dating of rocks on the surface, which is just mind-boggling that they're able to do it. But they can use argon isotopes that SAM can measure and then they compare that to potassium measured with the APXS instrument, and they can actually come up with potassium argon age dates. And they've dated some of the rock material to be quite old, around 4 billion years old. And then more recently, they came up with an age date for some of the material at only about 2 billion years old, suggesting that some of the activity in Gale happened a lot later in Mars's history than you might think.
And so they had never planned to do that kind of dating on the surface of Mars, and figured out a way to do it?
Yeah, I think it was one of those things where they were aware that it was like a potential possibility, but they never promised it because they couldn't deliver to any requirement. But they were aware that it could happen. And so after the SAM instrument was selected and the APXS instrument was selected, the team, somebody proposed to become a participating scientist on the team, Ken Farley at JPL, to do this particular experiment. And so they did, and it worked, which is absolutely incredible.
I'm sure there are so many stories. I mean, they just celebrated, you said you're up to 1,850 in the book, and they just crossed 2,000, right?
Yeah, they just crossed 2,000. So the book, the one that's being published now, is guaranteed complete up through Sol 1512, and then as much as I could get up through 1800. the distinction is because there's only so much that is released where there's data released to the planetary data system. And that's as far as I got for sure in the book. But then as I was getting closer to publication, I could throw in things like the drill failure and other stuff like that.
So how did this turn into 2 books then?
Yeah, so about that, I I had expected to write this book in about 2 or 3 years, and it had gotten into the fourth year, and I was like, I am not finishing this. And so I asked my boss for permission to take a 3 month sabbatical to finish the book. And I did that in the first 3 months of 2017. And I was getting toward the end of my sabbatical and I still hadn't finished. And I was like, this is what is going on? And I finally realized that I'd accidentally sort of written 2 books. Um, and I'd been having a lot of trouble with the structure of the book because the parts where I was explaining the engineering go into a lot of detail, and they don't have much narrative structure. They're like they, all those chapters have a repeating structure to them about sort of a basic description and how it works and the scientific background and how they found that it operates on Mars and any anomalies that have happened. And that structure repeats for all of the instruments, but there's no story there. And then meanwhile, I was also trying to write the story of the surface mission and the science and everything. And I was having a terrible time fitting those 2 things together. And I realized that what I actually had was separate books. I had a book about how the rover worked that isn't very narrative. It's more descriptive and reference material. And I had a second book on what the rover did, which is narrative. It's about the adventure of exploring the surface, about the problems along the way and the discoveries made and how the science fits all into that. And so that'll be the second book, which will hopefully be out around this time next year.
So it'll come together a little more quickly.
Yeah, because I've already written more than half of it, and I've done all the blogging that I've been doing on the rover mission at planetary.org/blog. I write updates about every 2 months, and so all of that coverage will help inform the book that I'm going to write. But then I'm also interweaving science results into it in a way that isn't. You can't write about the science as you're writing about the mission because you don't know what the science discoveries are yet. And so it's a fun opportunity to put the science results into the context of when the rover saw certain things and took certain measurements and stuff.
Now, we've enjoyed the science from Curiosity for about 6 years now. I guess 2012 was when it landed. How much longer do you think we're going to be able to continue receiving science from it?
Well, there's no particular reason to think that the rover there's nothing that's limiting the rover's life except for its power. So for a while, people were worried about the wheels. The wheels aren't a problem anymore, but the power situation is something that will kill it eventually. And you might think, well, they used to say that about Opportunity, and look how long Opportunity has lasted. But Opportunity is solar powered, Curiosity is nuclear powered, and there's no way to refuel a decaying plutonium pile. It is going to get down to a very low power situation in about 14 years from landing. So, its power is already declining. It doesn't really affect the rover all that much yet. And as the mission proceeds, they also get better about estimating power consumption so they can get more done on the same amount of power. But in about 14 years from landing, the rover will be down to about 50 watts per day, or 50 watts, being generated at once by the radioisotope power source. And that's currently what the rover needs just to stay alive, never mind doing any work. And so unless they come up with some major improvements to efficiency, after a while, you're just not going to be able to operate. You're certainly not going to be able to drive or operate the arm. Those are two of the most power intensive things. And so you might see a period where the rover is mostly stationary for long periods of time, but then can kind of spend a little while slowly crawling to some other spot, and then is mostly stationary for a long period of time as they trickle power into the batteries.
Now, just to switch gears briefly, we're just around the corner from another mission heading off to Mars. Can you let people know a little bit about that?
Yeah, so that's Mars Insight. And I actually got a chance to go into the clean room last week and see Insight almost all packed up for launch, which was pretty sweet. Insight is a completely different mission. Insight is a lander. It's built on the same rough blueprint as the Phoenix lander was, except that it has much bigger solar panels. It's designed to be a geophysical mission. Its goal is to look into the interior of Mars, kind of like Juno at Jupiter, where its goal is to understand the interior structure of Jupiter. And so it has two main instruments. It has a seismometer and a heat probe. And the goal is to measure how fast heat is coming out of Mars, is conducting out of Mars. And then to try to use Mars quakes to figure out the surface of the crust, to figure out, the thickness of the crust and whether there's anything interesting happening crustally. They'll be able to count the impact rate, the detectable impact rate onto the surface using the seismometer.
That's amazing.
Yeah.
Right? They're going to detect meteorites striking the surface around the lander.
Yeah. I don't know to what distance. Obviously, the distance, you can detect things to a longer distance if it's a bigger impact. So that'll be an interesting result. And then they're going to use radio tracking over a very long period of time to measure a minute wobble in the rotation axis of Mars that you would expect to be caused by there being a liquid outer layer up to the core. We think there's probably a liquid outer core, but this would be a different line of evidence to confirm it. And so when InSight lands, there's going to be a period of about 4 months where they're going to be setting up all the instruments and getting the heat probe into the soil. And then the lander is going to sit absolutely still for almost 2 years and just sit and receive and broadcast radio, but otherwise not move at all, because the experiment, they'll swamp the delicate things they're trying to measure if they move anything at all. So they'll just be completely still. And moreover, they're going to be landing deliberately in the most boring flat place on Mars. So it's not going to be the most thrilling mission.
Right.
It'll be interesting to follow in the very beginning when they're landing and setting everything up. And then, but it'll be the results, science results will be very cool.
But so it's not going to be like turning, looking around, moving any cameras, digging around, none of that stuff. It's just going to be sitting there and just listening with its
not
feet.
After that first 4 months. They will use the camera on the arm to take a full panorama, and so we'll get that 360-degree view that we're accustomed to getting. But there's no point in doing that again, and then once the science part starts, you actually definitely do not want to move, and so you're done.
Does it have a microphone?
It does not.
Because isn't that like the Planetary Society's just dream, is to put a microphone on the surface of Mars?
It's one of the things we're super into, but I believe there's now a microphone on the SuperCam instrument on the Mars 2020 rover.
Okay.
So we should finally be getting a microphone on Mars by then.
Good. Well, I'll just keep asking, because I want to know. I want to hear audio.
Me too.
From the surface of Mars. I want to hear the wind blowing.
Yep.
And I don't want to hear
and
a
the weird
simulation
sounds of
it.
your robot arm doing
turning
things.
Yeah, that would be great. All right, Emily, once again, hold up the book so people can see, and then we're going to give them very specific instructions, because if this sounds like a book that you want to read, and of course it is, you should go to Amazon.com, search for her book.
Search for The Design and Engineering of Curiosity
by Emily Lakdawalla, and put in a pre-order, and that will send all the right signals to Amazon, to the publisher, to all parties involved, that this is the kind of thing that there should be more of, and Emily will rocket up the charts.
It's currently the #1 new release in aircraft design and construction.
Let's see if we can get you the Weekly Space Hangout bump to other to other categories. All right. Emily, thank you so much. Congratulations on the book, and
thank you so much for having me.
Let us know how it goes.
Check me out at planetary.org.
Right on. See you later.
Cheers.
All right.
I want to read the book.
Well, gotta wait.
Gotta go get a book.
All right. Now let me cue up the rundown. Here we go. I'll be all right. Welcome to the Weekly Space Hangout for Wednesday, April 11th, 2018. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about a hotel in space, question mark, and a monster flare striking Proxima B, and the strange NOAA regulations that stopped the broadcast from a SpaceX launch. Joining me this week, we've got Dr. Morgan Renberg, the Director of Scientific Presentation at the Fort Worth Museum of Science and History. Morgan, welcome.
Hey, Fraser. Hey, Kim.
Let's see. And we've got Dr. Kimberly Cartier, Earth and Space Science reporter for EOS Magazine. Kimberly.
Hello, Fraser. Hi, Morgan. Happy podcast day.
Oh, I was worried you weren't even going to say it.
Of course I'm going to say it. That's my catchphrase now. If I have a catchphrase, that's what it is.
So Paul is out this week, but the three of us will hold the fort, and we have a great interview from Emily Lakdawalla from the Planetary Society later on in the episode. She, of course, used to be on the Weekly Space Hangout all the time, but then has been writing a book all about curiosity, and you'll get a chance to hear all about that later on in the episode.
If you're curious, you should keep listening.
If you're curious. Now, before we get into this week's news, I just want to remind everyone to check out the Weekly Space Hangout crew. This is, of course, the community that joins us every week when we do the show. Go to wshcrew.space. And if you're listening to this as a podcast on iTunes or Stitcher or however you get your podcast, if you could leave some kind of rating, a perfect rating, that would be awesome. The more people who see these ratings find out about the show, the more listeners we get, the better guests we can get. It's this self-fulfilling cycle. So you can be a part of it and leave us a rating wherever you listen to your podcasts. All right, let's move on. Kimberly, I'm going to start with you. You stole my story for the week, which is fine because it's awesome.
It happens to be about exoplanets.
Well, and you are the exoplanet expert, so I think it would mostly just be me mangling it, and then I would just look to you, waiting for you to fix my mistakes. So
sometimes I don't feel bad about stealing stories when they're about exoplanets. Anyway, so it turns out that Proxima b, which of course is the somewhat Earth-sized planet around our nearest stellar neighbor, Proxima Centauri, turns out that this planet probably isn't so friendly to life after all, which I don't think is a terrible surprise to any astronomer. I think mostly people have been trying to invent ways that it could be habitable despite all of the odds. But even though this rocky planet is in the habitable zone, it's around an M-dwarf star, which generally speaking are a lot more active and have a lot more stellar flares and UV radiation than do stars like our sun. And so the argument and the hope has been that there's been some mechanism that either the star is more quiet than we thought or the planet is more protected than we thought. But new observations of Proxima Centauri show that there may be up to 5 ginormous super flares of this star every single year, as something like 10 times larger than any other flare that we've seen come off Proxima Centauri in the entirety of us observing it. And these flares are strong enough that it would strip, I think, 90% of any ozone from an Earth-like atmosphere in about 5 years.
Yeah. This flare that they detected, I think it was about 2 years ago, was the bright one.
Yeah, so the first one that they detected was something like 2016, but in the 2 years since then, they detected 23 more super flares.
So it was bright enough that you could actually see it with the unaided eye.
Yeah, it was a flare that was bright enough you could see just without a telescope that the star was brighter. And the amount of UV radiation that came off of these flares on average is about 100 times stronger than you need to kill even the most UV resistant microbes we have here on Earth. It's incredibly strong, and unless there is some anomalously large magnetic field and giant shield of some sort protecting this planet, it's very likely that a lot of these super flares would be impacting on any sort of atmosphere or surface.
So are we seeing all of these super flares now because Proxima Centauri has some sort of solar cycle like the sun does, and really that this would be something we would have seen, 10 or 15 or 20 years ago if we'd had the capability of seeing it? Or is there something special that's just a random event right now?
That I'm not entirely sure about. I'm not entirely sure that we've looked at Proxima Centauri all that closely for any type of stellar cycle. And in fact, we haven't seen lots of cycles like these on many other stars except for the sun. So it could just be, the past few years have been particularly active. It could just be that it's always been like this and we haven't been looking, or the orientation of this triple star system hasn't been right, or we just haven't cared too much. It could be any of those things, and I'm not entirely sure what the answer is.
I mean, I guess before the discovery of the planet, we
it was
knew
a red
it was
dwarf
a red
star.
dwarf star, and there's lots of them out there. It's close, and that's
and it's
neat.
close, but yeah,
apart from
there wasn't
that.
too much interesting about this.
Is exoplanets the best thing to happen to stellar astronomy? Because
not
suddenly
gonna
we
say-
care a
okay,
heck of a lot about all of these stars.
I'm not going to say that, because then all of the solar and stellar astronomers are going to be really pissed off at me. But I will say that telescopes like Kepler, which stared at stars for a very, very long time, also provided a wealth of information about the stars themselves and not just the planets that they hosted. In some ways, Kepler was the most dedicated stellar astronomy mission that NASA's ever done, and provided a great deal of information about, star spots and flares and how active other stars are, and rotation and astroseismology, and all this other non-planet stuff. So
until about 4 days from now.
Until about 4 days from now, and then Tess is going to do it even better. Because yay.
But how long would a star? I mean, do we know sort of where Proxima Centauri is in its life cycle? Is it a fairly young? Like, I know it's a flare star, and obviously it is, but is it young in its cycle as a red dwarf star, or is it?
So here's the thing: is that when a red dwarf star is young, within the first few million to 100 million years or so, it's easy to tell that it's young because it still has lithium in its atmosphere. And lithium burns incredibly quickly and at not too hot temperatures. And so any star that starts with lithium will burn through it pretty quickly. So if it's still there, it's pretty young. After that, with M dwarfs, it's incredibly difficult to tell. So it's not young, but who knows how old it actually is. And you have to include the ages of the other two stars in the system to actually figure that out. Probably a few billion years.
And is there some point where even the most grumpy flare stars settle down and become reasonably habitable, or will a star like this just keep flaring forever?
I mean, eventually it'll cool down and it'll stop burning hydrogen in the core.
In a trillion years.
In a trillion years, it'll stop burning. It'll stop having the energy to cause these flares, and it'll just sort of like peter out eventually, but not for a while.
And this is, I guess, the sadness for the people hoping for life out there in space. The vast majority of the planets, the Earth-sized planets that they're finding out there, are these planets orbiting, like the TRAPPIST system. These planets orbiting around red dwarf stars, and they suck.
That's the difficulty, is that sometimes they suck. It's true. But not all red dwarf stars, M dwarf stars, are as flary as this one. Some of them are rather quiet. Some of them only flare a little bit. Some of them only have a little bit of extra UV radiation. And we're not entirely sure why that is, why some are strong and some are not. But on the balance of it, there might be some planet in an M dwarf habitable zone that might not be wiped out with flares. Maybe.
So should we cancel the Breakthrough Starshot mission and not send a spacecraft to Proxima and instead go somewhere else?
What are you talking about? Why would you say that?
No, it's still on.
I want to go to Alpha Centauri. I don't care.
Yeah.
I don't care if there's life on the surface or not, or if it's subsurface microbes, or if there's some incredibly mutated microbes that have the most powerful UV sunscreen that you could think of. It's SPF a bajillion. I don't care. Yeah. I still want to go to Proxima Centauri, so don't cancel Breakthrough Starshot.
All right. That was close.
If you're listening,
if they're listening, yeah.
Don't cancel. I still want to go.
I guess, do you think that this research is going to have any impact on sort of the way people are looking for planets? I mean, for you, you don't care whether there's life there or not. Is that habitability really driving a lot of the exoplanet research at this point, or not so much?
I think that I will say within the exoplanet community, there's the habitable people and there's the not habitable people. The habitable people want all of the information on what can make a planet habitable, and they want to find that Earth 2.0. A lot of other astronomers just want to know why a planet is the way it is, what kinds of planets can be there, and what can they do. And some subset of that is, some of those planets could be habitable, could have liquid water on the surface, and maybe even life. But we don't know why our solar system looks the way it does and has a habitable planet, when there's two very similar ones that aren't habitable. We don't know that either. So there's all sorts of motivations for exoplanet research, and some of them just happen to be habitable zone planets.
Now, did you look into the actual instrument that they used to make their detection? I don't know if you saw this.
So it's a telescope called the Every Scope, which I have not actually heard of.
I hadn't heard of it before this announcement.
It is apparently a very cool thing, and they also followed it up with the HARPS spectrograph, which is a high-res spectrograph that got all the information about the UV, and they performed a 2-year monitoring campaign of this star and caught all these flares. Really cool.
So it monitors an 8,000 square degree field every 2 minutes.
It's pretty freaking awesome.
Yeah. So it's about 100 degrees of the sky, and has 36,000 pixels. And so this was just one of the stars that it detected doing these flares, but it looks like it's able to do lots and lots of them. And it's sort of go ahead, Morgan. I can hear you.
I was just going to say, a lot of these super wide field of view Earth-based telescopes looking for exoplanets and stellar activity are actually incredibly sort of MacGyvered together. I've seen a number of these that are basically off-the-shelf camera chips with a off-the-shelf SLR lens flipped upside down and glued to it. And if you ever look backwards through a pair of binoculars or something, you see this weirdly distorted image. And it's really cheap to take a cheap sensor and a cheap lens and glue them together, and then use software to sort of undistort this super wide field of view. And they can create these things and put them in little observatories out in the middle of like the Arizona desert for like thousands of dollars, just like peanuts compared to what it would take to build the cheapest instrument for an actual astronomical observatory.
And I think it gives us that glimmer, that sort of glimpse into what the future is going to look like when we get things like the LSST, which is the non-MacGyver version, where it's a gigantic telescope designed to take this wide field view at a very deep level night after night after night and really build up that view of the night sky and look for anything that's going to be different. This is the kind of thing that LSST would find. And so to be able to have an instrument that was able to do it on a shoestring and turn up a really interesting piece of science, I think is just absolutely fantastic. So
yeah, most definitely. And I mean, like, we still need to look at Proxima b. We still have to study that planet. And it's one of the best planets to do this for because it's so nearby. But I mean, now that we know that super flares are a common thing in that system, probably striking that planet very, very often. That's a pretty firm data point right there. That's a pretty solid fact about that system. So anything else that we observe about that system has to be built around that. So if we observe that planet and we see that there is some sort of tenuous atmosphere, that might tell us that there's some sort of volcanic outgassing maybe. Maybe there's something turbulent happening on the surface. Maybe there's a signature of water, which means that there might be something subsurface, and then who knows? So we have something almost solid about this planet, and now everything else we can build around it.
Yeah. Morgan, tell us about a space hotel.
Yeah, what up with that?
Yeah, so one of the lines we've kind of been parroting again and again when talking about these new classes of reusable rockets is that they're going to enable a new kind of mission, new opportunities for new groups to do new things. But we haven't been able to really say what those new things are. We've talked a little bit about SpaceX's plan for a global internet. We've talked about the idea of launching massive amounts of CubeSats. But what about a space hotel?
That was next on my list.
Yeah, I know. That's right. This is a company called Orion Span, and they're planning to launch a space hotel called the Aurora Station in 2021 to take in the first guests in 2022. And to get a chance to spend 12 days on Aurora Station, it's actually kind of a steal. You only need to pony up $9.5 million.
For how long?
For 12 days.
For 12 days.
And if you're kind of on the fence about that, it's only an $80,000 deposit to hold your place in line right now while you think about that. So if, a Tesla is not good enough for you and you're thinking, I don't need to buy a house, then maybe 12 days on a space station is what you need. And that'll buy you some time to earn the rest of that $9.42 million that it'll take to actually do the journey. But in all seriousness, this is actually a pretty cheap price. The Russians have ferried a number of private citizens to the space station in the last couple of decades, and they've charged sort of anywhere in the neighborhood of $20 to $40 million for a similar stay. So here we're seeing a price that's 2 to 4 times cheaper than that, and that includes launching the station and building the station and all of that stuff to get it up. It's still a lot, but it's less than if you wanted to go to the ISS.
Now I'm going to just go ahead, Kimberly.
Oh, I was going to say, so when I go and I look and try and book a hotel, one of the things I look at is amenities. What will this space hotel provide for me, aside from spectacular views?
Well, you do get free high-speed internet back to Earth.
Ooh.
So if you wanted to spend your 12 days in space browsing Facebook, if it still exists in 2021,
well, you'd live
or
stream.
Skyping with your family, you can do that. You also get 16 sunrises and sunsets every day. That's something that no other resort on Earth can offer. And just to be able to go, you get a 3-month astronaut training course. I assume sort of learn to find the barf bags and how to, parachute from outer space in case things go wrong. And you join three other guests and 2 crew members for your 12-day stay.
Now, I'm going to just look at my calendar and see that here we are in 2018. You said 2022?
2021 is what they're claiming for the launch, and 2022 for the first guests.
So in 3 years, they're going to build and launch a space station.
Yeah, I think that they took all the fast engineers away from JWST.
Yeah. I mean, come on. Like, JWST needs another few years worth of just shaking.
Yeah, I mean, there's no way that this thing is going to launch in 2021 or take guests in 2022. But just the fact that someone has bothered to put together a business plan to suggest that this is possible and kind of done enough thinking about it to even come up with a date shows you that there's an opportunity here that wasn't available in the past. Because if you have to build your space station and then launch it on a $500 million Delta rocket, $10 million isn't going to get you anything. But if you can launch that same hotel on, say, a Falcon Heavy, or maybe you can miniaturize it enough, use the sort of inflatable technology like Bigelow Aerospace has, maybe you can fit that onto a Falcon 9, and you hope that by 2021, reusable Falcon 9s are going for a lot less than they are today, then you can kind of find a way to maybe convince yourself that the numbers would work.
All right, I just want to pause and rewind for like a minute back, and you just said launch a hotel on a Falcon Heavy. It's like, this is the world we live in. We're launching hotels now, which is
not just a hotel. The if
What do you mean?
if
What?
it goes well, they're thinking that they will offer permanent rooms, so you can buy a condo on the Aurora station in the future. They're not talking pricing on those condos yet, so don't plan your pre-leasing party quite yet. But they're thinking that a phase 2 of this program could be permanent opportunity to stay in orbit and rocket rides back and forth, which would make for a heck of a commute.
Yeah.
I gotta lock in my mortgage rates now.
It'd be a quick landing. I mean, I can see. All right, let me think.
Okay.
I've been doing this job for a long time. And
I don't know how to react to this.
And I have definitely seen this kind of proposals before. And I think you brought up the Bigelow. There have been a bunch of others. The Russians have said they were going to do this kind of thing for space tourism, in addition to what they were doing with the International Space Station. So, I mean, I guess the question is, I mean, I think the Falcon Heavy isn't the machine that's going to do it, but for the BFR, then it sounds utterly feasible, right? That you could launch, we've talked about this a couple of times, the BFR, just the price to launch this thing is in the tens of millions to launch their biggest rocket, and the only price is the fuel, and the thing will have an enormous cargo capacity and ability to launch into low Earth orbit. So I can totally see, but then you've got to build a space station, you've got to ship it to SpaceX, got to shake it around a lot. Human lives are this has to be a human rated machine that you have to build, and this isn't a Bigelow thing. Anyway, I have so many lines of skepticism, I don't even know where to start.
Well, let me ask you a question. I'll pose this to both of you. So a trip to space aboard the Virgin Galactic or one of the Blue Origin trips is probably going to cost somewhere in the neighborhood of $250,000.
Yeah.
That's the price tag that Richard Branson's put on Virgin Galactic. It's easy to imagine Blue Origin will fall in the same realm, and that nets you about 5 minutes of weightlessness.
Yeah.
So, on a dollar per minute of weightlessness basis, the 12 days for $10 million seems like a pretty good deal. So, does that seem like a good?
Yeah, but it's not.
Seem like a good trade-off to you?
I mean, you're asking me, like, do I want to pay for a house in suburbia or pay for a penthouse in Manhattan? They're both out of my reach. Like, those are dollar amounts that I cannot comprehend in my daily life. Don't get me wrong, staying in space for almost 2 weeks would be freaking awesome.
Yeah.
Like, that's half the reason why they're doing this, is because it's just so awesome and everyone would want to do it.
Yeah, I think they'll have a lineup out around the block of people who would be wanting to do it. And I guess that's the point, is that if they've done the math and they think they can launch it for this price and they can service it for this price, then there will be a lot of customers who will be glad to sign up and do it.
They'll be on the right side of supply and demand.
Yeah. And the question just is, can you get these launch costs down? Can you get these? And I don't even know whether the Falcon Heavy does the trick. I think you need to get to the BFR to actually be able to do this. And we're still looking at 2021, 2022 before the full stack of that thing is going to be launching. So.
Okay, so we're all going to pool all of our savings together and get on the list and have a vacation?
No.
This is what I'm hearing.
No, see, this is the thing. No. I want to, because space tourists were going on the Soyuz, right? Like when all the tourists who've gone up to the space station now, they've gone on the Soyuz, which is like the most dependable, longest launching space capsule ever built. To turn around and have something that's going to go this quickly, I'm going to wait for other people to go first. But then I'll totally do it. I would totally do it.
We got to get on the waiting list now, Fraser.
I got to get my $80,000.
It's just $80,000.
Okay, everybody, we're going to need to put a lot of ads into the Weekly Space Hangout. I just apologize in advance, but it's what it's going to be, and you'll know that all that advertising is for us to be able to get that trip to space.
Give you a live show from space.
Yeah, we'll totally do a live stream. Be good. This episode of the Weekly Space Hangout brought from space. That's
As
really
we're hanging out in space.
yeah. See, really, that's its destiny when you think about it.
Yes.
All right. As always, I've only got a few seconds left, so I'm going to go quickly here. So, turns out a couple of weeks ago there was a launch of an Iridium, a series of Iridium satellites by SpaceX, and when they went into the launch, they got through up to the first stage, and as they switched over to the second stage, they sort of during their live stream, the folks at SpaceX were like, "Oh, we have to shut off the stream." It turns out there's a NOAA law that that we're not allowed to continue streaming because we didn't get a license in advance, and it turns out that if you're going to stream a view of the Earth from space, you have to go through NOAA as well as whatever you need to do with the FCC to get a license for your launch. And the thinking is that Tesla hadn't kind of run into this until they launched. Sorry, SpaceX hadn't run into this until they launched the Tesla car, which had full live stream views of the Earth, and they got a slap on the wrist from the folks at NOAA. And actually, there was some confusion. So NOAA was parts of NOAA weren't actually sure that this license was required. Others did, and so when they did this most recent launch, they ended up having to cut the transmission. Then they did the launch of the Dragon on the CRS-14 launch, and on that one, because it's a NASA launch, they don't have that restriction, even though it's the same Earth.
Wait.
Yeah, so it's fine.
It's just NOAA, but not NASA?
Right. So if it's a private launch, then they need to get this license. If it's a government launch, then it's okay. And so they needed to cut the feed.
I guess that's where my confusion comes in, because NOAA's a government agency too.
Yeah, but they weren't launching
a NOAA satellite.
Right.
Oh.
So if they're launching a NASA, so I guess the point is that NASA already has these licenses, already has the regulations. But I mean, the resolution of the camera on board, the upper stage is, one continent per pixel. Like, it's not very high resolution, right?
Like, what are you going to tell from there?
Yeah, like there's Area 51 or something. So
yeah, I don't think anyone thinks that this is a good thing. This is an example of a rapidly evolving field outpacing legislation, and I wouldn't be surprised to see a provision slipped into a future funding bill that just writes this out with no discussion.
Yeah.
Because I don't think there's really any stakeholder hanging on to this. It's obviously not a national security concern. It's an anachronism of the 1980s when this whole new digital imaging thing was fancy and newfangled. And it obviously doesn't make a lot of sense today.
Yeah, but pretty much the only people going to space were governments. So
yeah,
who didn't need the U.S. government's permission anyway?
Yeah,
right. But you can see, the people, the conspiracy theorists on the internet just kind of went berserk because, governments were shutting down live feeds to the of the launch. So I think that's the part that I found is pretty funny. So apparently yeah.
Sorry, that part is like, you're complaining because you only got to see part of a live rocket launch. Like, that's an incredible amount of entitlement. Like, we didn't have this.
So they admit that first stages are real, but they deny the existence of second stages. I guess that's the point.
But we haven't even had this for a decade, and they're going to be like, "Oh, government taking away my second stage stream."
Yeah.
How dare they?
I mean, I absolutely love the coverage of these SpaceX launches now, where you do see this rocket on, you see a nice camera view of the thing launching. There's cameras on board the rocket. You see the separations. Now we saw with the Falcon Heavy, other parts of the rocket coming back to land, the view from the second stage, and now the view from a car
and then
in
it fell
space.
Then it fell into a wormhole.
Yeah, for that
There's
one.
nothing
But
after that.
This might end up being kind of a moot point because we're all going to stop caring about these launches pretty soon. 2018, SpaceX is launching every 2 weeks. That's only twice as often as I go, or half as often as I go grocery shopping.
Yeah.
And so I don't feel the need to live stream every trip to the grocery store. And I think soon, even if SpaceX is producing these videos, we'll only be tuning in when, the BFR launches or something like that, and not your sort of weekly run to space.
Oops, it's Tuesday again. It must be another SpaceX launch.
Yeah. Well, and even like some of these most recent ones are not that exciting because they're not reusing the boosters. They've just been going through these older boosters because they're switching to this new version 7 of the rocket, which has a bunch of new bells and whistles, and so they don't need these older boosters, so they're not trying to conserve them as much. So I think it's going to be a bit of sort of old school rocketry for a while until, as you said, the next Falcon Heavy goes off, the BFR goes off, or we see some of this new hardware start to fly and do some of its fancy
That
landings.
new Falcon 9 could launch by the end of April. In SpaceX time, that's probably like June. But, we're coming up on the launch of the Block 5 very soon. And those are supposed to launch a dozen or more times to space before being scrapped. And so that'll be pretty exciting to watch the 4th and 5th and 6th landings of the same rocket to see how it performs.
All right, let's move on to our interview. Great interview with Emily Lakdawalla. All right, let's wrap things up. Morgan, shamelessly self-promote something interesting that you worked on this week.
I'm actually going to pre-promote the fact that I'm going to the launch of Insight in May.
Man.
It's actually over the weekend of my birthday, and so I'm going to go out and join Sandy in California to watch to launch. And I had sort of put it to the back of my mind, but hearing Emily talk about it has me really excited to see another launch happen, and really a kind of innovative look at Mars.
Are you going on to, like, are you going to go to the press area at Vandenberg, or are you going to just do this from like a beach or something?
Yeah, no, we're just going to do it from a beach. I got our act together far too late to do that. And at Vandenberg, the public viewing area and the on-site viewing area are not that different. And so in terms of perspective. And so I think we'll have a pretty good, it's a night launch. It's like a 3 a.m. launch. And so I guess the odds of launching are very high. The odds of seeing it are pretty low because it's often very foggy on the California coast at 3 a.m.
Right. Kimberly.
Yeah, so on Monday there's a launch, and I know we're just talking about how humdrum SpaceX launches are, but on Monday they're launching something
Very
that's
important.
kind of cool that I might have been waiting for many, many, many years.
Yeah.
It's the TESS satellite. It's Kepler on steroids, and it'll be my new BFF. And so I've been delving into that all week in preparation for the launch. And
So have
it's just
I.
been all tests all the time.
Yeah.
And it's been a great week.
And NASA has released a whole bunch of really great videos to sort of show you its orbits and how it's going to be scanning the sky.
Yeah, that video about the orbit and how the orientation is completely new is something that I didn't even know about TESS until I started just taking a really deep dive into it. So definitely go check out all that stuff, and hopefully, crossing my fingers that SpaceX launch will be just as humdrum and normal as
nice and safe
as we expect, and not going to explode on Monday evening. There'll be an article from me bright and early Tuesday morning all about it.
Excellent. There's actually going to be a video from me probably at the same time as well. I actually have to write 2 scripts for the video that I'm doing because Chad's going to be editing it as the rocket is launching. So there'll either be if all goes well, it'll launch soon, or it just launched, and here, let's watch the launch video. So.
Well, for me, it's more of it launched, and I can't publish until Tuesday morning anyway, so the timing is not that big of a deal. But if it doesn't launch, or if it explodes or something, then that's a whole different ballgame.
So my just quick bit of shameless self-promotion is we just just seconds after I finish this episode of the Weekly Space Hangout, I'm going to push live our newest episode of The Guide to Space, where we talk about living, working, exploring lava tubes on the moon and Mars. And we got a bunch of really great sort of cool video and photographs directly from the researchers who are exploring caves on Earth, building simulations of caves, proposing missions. We got a lot of really great stuff that you'll have never seen anywhere else. So I'm really looking forward to this episode. It'll be live in an hour, I hope. All right, let's wrap things up. Thanks, everyone. Thanks to our special guest. Thanks to my co-hosts for joining me this week. Sorry, Paul, you missed a good one. And everyone watching live, we'll see you all next week after Tess is launched. Bye.
Now you've jinxed it. Thanks.
Oh, there you go.